In this short video, what we're going to be looking at is how to use experimental data to find the Kc for esterification. So the experiment we're going to be using is a titration. Now, for my apparatus here, for my storyboarding, I use the amazing website called Chemix. I really urge you to go have a look at that for when we start to designing experiments. So here's a question explaining that a mixture was left to reach equilibrium and it's put into a flask and made up to 250 cm³ with distilled water. And a sample of this, using a pipette, was taken out and it's been titrated with sodium hydroxide that's in a burette. And what I've done here is to storyboard. So I've taken pictures of the apparatus from Chemix, taken the information from the question and put it into a diagram. It's a lot easier to see. Visual imagery is a lot easier to see, especially if you're asked to describe an experiment, how you'd find the Kc of an ester. So what I'm doing here is filling in the volume of the sodium hydroxide that was used for titration, the concentration of the sodium hydroxide that was used from the titration, and also the volume of the mixture that was taken from the equilibrium mixture and pipetted into the conical flask. So the next step, once you're doing the storyboard, is write an equation for the titration. So we're working backwards. We're looking at the information from the data they've given us. So we can work backwards, looking at the amount of standardized sodium hydroxide needed to neutralize the acid that was left behind at equilibrium. So some of it will have reacted and some is left behind in the equilibrium mixture. So to work out the amount of sodium hydroxide, it's concentration times volume over 1,000 to convert the volume into decimeters cubed. The concentration was 2 times 10 to the minus 1. The volume was 3.2 centimeters cubed. We divide it by 1,000 to get it in moles, and to get it into moles and convert the volume into decimeters cubed. So the moles of the sodium hydroxide is equal to the moles of ethanoic acid that was left behind in the titration mixture. And that works out at 6.4 times 10 to the minus 4 moles. And that was the amount of the ethanoic acid that was present in this 10 centimetre cube sample of the original 250 cubed in the equilibrium mixture that was in the graduated or the volumetric flask. So back to my storyboarding. What we've done here now is, because we know the amount of ethanoic acid that we've just titrated, the 10 centimetre cube sample, to find out the amount that was in the original mixture, we need to times it back up. We took 10 centimetres cubed out, so we need to times it by 25 to get the actual number of moles that were there at equilibrium. And that comes out to 1.6 times 10 to the minus 2 moles. So now write out the equation again, and then we're going to use something called ICE. ICE is initial, change, equilibrium. So here are initial amounts from the exam question. Here we were given the initial amounts, so they have gone into the initial amounts. We had no ester, no water. The equilibrium amount of acid we've just worked out. And therefore the change is the difference between the initial and equilibrium. So we have lost 6.4 moles of the acid, and because the acid reacts with the alcohol on a 1-to-1 ratio, we must have also lost 6.4 times 10 to the minus 2 moles of the alcohol. And therefore, because the moles of acid forms ester on a 1-to-1 ratio, we must have formed 6.4 times 10 to the minus 2 moles of ester, and also exactly the same number of moles of water. So now we have our equilibrium amounts. We can now start to add these in. So the difference between the initial amount of alcohol and what was lost is now 5.6 times 10 to the minus 2 moles of alcohol remaining. We started with 0 of ester, we've added 6.4, so in total we've got 6.4 times 10 to the minus 2, and because they react on a 1-to-1 ratio, exactly the same number of moles of water. Now what you must remember is for equilibrium we have to get the concentrations, but because the moles of acid and alcohol at the start, we've got 2 moles on this side and 2 moles on that side. When you have equal moles on both sides, the volume cancels out, so we don't need to work out the molar concentration because the volume will cancel out. So here is our ice table, and the final step is to write out our equilibrium expression and then to write out the values. So remember to write out the expression for Kc. It's the concentration of the products, which is the ester and the water. They're the products. And then we divide those by the concentration of the reactants. And the concentration of the reactants is the concentration of the ethanoic acid divided by the concentration of the alcohol. Notice I haven't put the chemical formula in because it's a lot faster to write simply acid and alcohol. And you can use this expression for any esterification. And now all we need to do is to put our values in. So the concentration, or the number of moles, the amount of ester, is 6.4 times 10 to the minus 2. In this particular case, so is the amount of water. It's important to note that if we had some initial ester and water to start with, we were our equilibrium amount, we needed to add those together. Divide by the amount of acid, which is 1.6 times 10 to the minus 2. Multiply that by the amount of alcohol, which is 5.6 times 10 to the minus 2. Now, before you start diving for your calculators, we can cancel out the 10 to the minus 2s. And that makes it a lot faster to put that into your calculator, enter that into your calculator. So the answer comes out to 4.57. There are no units because the units cancel out. And the number of significant figures is 3, because throughout the data that had been given to us was to 3 significant figures.